Hi, welcome back. In this episode, we will talk about or describe a simple gossip protocol implementation or modeling with TLA plus. So, so gossip protocols are typically used in a distributed system design with, so basically in a large cluster distributed system, you may have tens to hundreds of potential servers working together to provide a collective service, usually in a geodiverse environment for to maximize uptime, right? So in the cloud environment, typically you want to have the nine nines, the uptime requirements. So, but then for the service in the cluster to provide the service collectively, they kind of need to know their neighbors really, right? So I guess the one way to solve the problem is to use a centralized server. You have basically everybody talking to this one server in the cluster that knows about everybody. But that kind of introduces a like sort of then that sort of single server becomes the bottleneck in the system, right? So the server really need to be able to, in some sense, self-discover, and then this is where the gossip protocol comes in. So as the name implies, the gossip protocol is sort of like gossiping in your among your circle of friends, right? So for every node that comes up, it would pick usually n number of server to gossip with, and then among the gossip they would talk about basically who update each other on the latest of all the other servers. So for every single server, the server keeps track of all the other server that it's aware of or has heard of. So that really is the premise here. And then actually, yeah, so I've got a diagram here that sort of illustrate what it looks like or what we're going to model in this chapter. So assume a cluster of three nodes, and then basically they could each pick somebody to gossip with, right? And then so the gossip is actually bidirectional, right? So when A initiates gossip with B, they both get up to date. They both update their local cache to the latest of what both party have, and then so they could initiate between each other, initiate with the other party, and whatever, right? At the same time, though, they can also increment their own version as well, right? So A is running along, and then it made some changes locally, and then so it bumps its version number, right? So the intent is when A talks to somebody, A would tell that somebody that oh, I have now been updated. This is the latest version I'm using, right? And then B would then start gossiping that information with all the other nodes in the cluster. So in this example, we're only going to constrain ourselves to a 3-node cluster, but in a real example, in a real world production environment, you can imagine this is going to be the number of nodes in the cluster is going to be much larger, right? So so the nodes can gossip with each other. The nodes can bump their own version number, basically update themselves and communicate that to others via gossip. A node can also restart. So the intent here is, again, in a large cluster environment, all the nodes operate independently, and they may crash, right? They may restart for a variety of reasons, really. And when it restarts, it needs to be able to sort of relearn the cluster topology again, right? So in a restart event, because we assume the local version, the local information is persistent, so A will remember. So if A restarts, A will remember what version it was at previously, but it will not remember the version number of all the other nodes in the system, right? And then so in a restart event, A need to relearn the topology of the cluster via gossip again. So in this simple example or modeling, these are the events that we allow, right? So for a given node, it can gossip with some other node, it can restart and lose, the neighboring information except itself, and it could basically bump its own version number. It could update itself and then communicate with others. So that's the example we will implement in this chapter. So the design part of it sort of, I guess the 3.1 here really explains what we just talked about, right? So each server has a version represent the current state. And then each server caches the version of all the other servers, basically in this case, versions. A pair of servers can randomly select to gossip. This is really to represent, A choose to talk to B, A choose to talk to C. But since gossip is bidirectional, the initiator versus the receiver doesn't really matter. We're just picking a pair to gossip. Yeah, and then we also talked about a server can restart, and restarting a server clears the server's own version cache, except itself. And the server is also allowed to update itself, so bump its own version number. So this is sort of a converging protocol, right? So as the system progress, you should expect the version number of all the server to be sort of going forward, right? That really is the design intent. And then that's also what we will try to verify as a liveness property for this model. So on the left, I have, I guess, the air quote, the implementation for the spec. And as usual, right, so I think we talked about in earlier episodes where the core skeleton of the spec is always an init function, followed init definition, followed by a next definition. And the only variable we have in this model or in this spec is a two-dimensional array of version. So as we talked about earlier, each server keeps track of its version as well as the version of all the other servers that it's aware of, right? So A will have a topology of all the servers, and then B will have a topology of all these servers as well, and C will also be that as well, right? So in this case, in a 3-node topology, we actually need a 3x3 table to keep track of everybody's understanding or awareness of the version of the other servers. So that's what this represents, right? So version is initialized to an array of servers, and then for each individual instance, it's another array of servers initialized to 0. So there's different data structures supported by TLA plus. In this example, we're using a function. So there will be another episode that we sort of go through what the supported data structure are by the language, but here this is basically, you could sort of see this as it's kind of equivalent to a unordered map, if you will. So it's kind of a unordered map of unordered map, and then with the value of a key, right? So that's really what it comes down to. So the servers is defined to be I think a set of strings, right? So S0, S1, S2. So it's a unordered map of unordered map, and with a key value, with the value of integers, the 0 being the version number. And now, then we define the actions, right? So going back to the state diagram here, for individual nodes, the allowed action is really to gossip, to restart, and to bump its internal version, right? So these are the 3 possible actions, and then the parameters will be different, right? So for gossip, we need to pick 2 servers. For restart, we just need to pick 1. For bump, we just need to pick 1 as well. And then so that's described using this, right? So so this symbol is the existential qualifier. And then so basically this is saying that so there exists a server I in servers, right? So server is the set that we provide the spec with in the configuration file. And so there exists a server I in servers, and then so we can bump the version of the server. Or there exists a pair of I and J in servers, and they can gossip. And finally, there exists server I in servers, where we can restart it, right? So in this next definition, the spec is allowed to pick any of one of these actions to take. Okay, so now we define, the sort of the skeleton or the blueprint of the protocol. Let's look at the actual implementation detail. So let's take a look at the definition for gossip first. So gossips take two parameter, I and j. Both are server names in the cluster. And what we're really trying to do is to allow the two servers to compare nodes, right? So they both have their own reality of the world, and then they're trying to compare nodes and see, who has the latest of the environment, and then they both take the latest from both sides. So version I here really is an array of all the other server I is aware of, and symmetrically, version J is the array of servers that server J is aware of, right? And then so what we're really trying to do here is in the let-in clause, so everything under let, our localized definition for the function gossip. So within here, update is defined to be comparing version I and version J. Again, they're both arrays. So we're comparing the two arrays entry by entry and taking the maximum, right? So that's what this line means. So now we have an updated array. We need to set it back to I and J. The semantic you can use in TLA plus is using except. So this is sort of the tricky part here. So you can't really assign. There's no assignment operator. So these are equality operator, right? So what we are really describing here is version A is the same as version, except with the ith entry replaced. But we need to replace both I and J, right? And then I define another one here where version AB equals to version A, except with J replaced as updated. And then so now version AB is the same as version, except I and J are updated to the latest. And then finally, we go back to the content under the in clause. And then so in here, version prime, so version in the next state is the updated version, right? So that's what the definition for gossip is implemented as here. So next, we'll take a look at the definition for bump. So again, version I is server I's reality of the world, right? And then more specifically, we only want to update its version, right? So version I represent that. But TLA plus, since it represents a system as a graph, it can go unbounded if we don't constrain the version number. Since in a gossip protocol, the version number can grow monotonically forever, really. So without a bound, the model checker would never know when to end. So the first conjunction in this definition here is to effectively limit the size of the graph, right? So we're stopping it at max version. So until we hit that, we will bump it. But once we are at max version, we disallow bumping, right? So we're bounding the state graph. And the second conjunction is updating, or maybe not updating, that's what version, we're describing what version needs to be in its next state. So we're only bumping server I, so we're updating version. So we're keeping version as is, except for the ith entry, which is the reality for server I. And then within that, we want to keep the value for all the other server except itself, right? Because we're only bumping our own version number. So that's what this definition, the second conjunction, is defined to do. We're only bumping I when I equals to I. And finally, we get to liveness. So to me, this is the most interesting part of the of TLA plus, and then the spec as well. So the spec defines 3 possible next actions. So bump, restart, gossip. But without any fairness description, any permutation of these actions are allowed or permitted by the spec, right? So we could get into a restart loop. It doesn't really matter, which server we're restarting. We could be restarting the same server over and over again. We could, restart the server, different server every single time, but we're still stuck in a restart loop. we could be stuck in a restart and gossip loop, right? So restart gossip, restart gossip. We could, be stuck in a gossip loop, right? So without that fairness description, there really is no guarantee on what the model checker can do. And this is actually by design, right? The model checker wants to explore all possible state, right? And then so if you describe certain liveness requirement, and then the model checker can say, wait, but if you're stuck in a gossip loop, or if you're stuck in a restart loop, then the certain property you have described are not met, right? So this is actually by design. So to verify a liveness property, we again need to provide a fairness description. And then so in this case, what we're really trying to verify here is over time, right? In a gossip protocol over time, the version number should converge. And then it's only meaningful when the version gets bumped, right? So in a live system, we expect the servers to be self-updating to with additional information or whatever, and then they start gossiping with each other, and this information gets propagated across, right? So the action we want to provide a fairness description for here really is bump, right? So we want to say that we want to ensure that bump gets called for all the servers, under certain guarantee, so then the system can progress forward, right? And then with that, then we can provide a liveness description where we're verifying that over time the version value in the cluster move in a certain direction, right? So that's what we're really trying to verify from a liveness property perspective, but we need to provide that fairness description for bump first. So that's represented by this clause here, right? So for all I, for all I in servers, right, we want to provide a weak fairness guarantee for the action bump. So again, so in another episode we'll talk about the difference between strong fairness and weak fairness. For now, just assume that, just sort of maybe take it as is, right? So we need to provide a fairness description, and weak fairness is good enough for now. And now with that, we can actually define our liveness property. So the liveness description states that there exists a pair server I and j where I doesn't equal to j, and the pair of servers always eventually make it to max version, and then they know each other have also made it to max version. So this is kind of the, maybe the cool part, in my opinion, of TLA plus, right? Like these kind of description that you could provide. So the box operator here means always, and the diamond operator here means eventually. So together they mean always, eventually. And then as the word imply, right? Like it just needs to happen once, really. Once it always eventually makes it, then it already satisfy the description. So in this particular example, if we try to swap these two operators, so you could certainly do that, right? So TLA plus spec also allow you to define eventually always, right? So if you swap them, with a diamond first and then the box second, then it becomes eventually always. It will actually fail this liveness property. So the protocol as defined, the spec as defined, will not eventually always converge to for any pair server converge to max version. And then this is because of the restart action that it can possibly take, right? So the restart will basically wipe a server's local knowledge of all the other servers, and therefore failing this liveness requirement, right? So for this particular spec definition, the replacing always eventually with eventually always will fail, because the restart action, because when you could be in some sort of weird restart loop where once you make it to maximum version, you restart, and therefore wiping the local definition, thus failing this definition here. But the always eventually is always true, right? Because the spec basically guarantee that we will eventually move forward, we will make it to this condition, even though it may not stay in this condition, but we will at least make it to it once. So that's it for this episode. Thank you for listening.